right, our next speaker this afternoon is River Schmidt-Eder, who's joined us this summer from Carleton College. River's been working this summer with Tony, and today he'll tell us about their project together, the role of compact galaxies in reionization.
Thank you, Gwen, for the introduction. Hello. Hi, my name is River, and in collaboration with Tony this summer, we have been constraining the sizes of high redshift galaxies in order to understand their role in the reionization process. All right, so first things first, reionization, what is it and what does it mean? Reionization is essentially when ionizing light ionizes neutral hydrogen in the intergalactic medium. And it matters because reionization is a phenomenon that's responsible for how our universe looks today. In the first 100 million years of the universe, ionizing light couldn't travel very far, always coming into contact with close-up hydrogen, which essentially made the universe opaque to it. A billion years later, though, as ionization began to take its toll, the universe started to take the shape that it has today, with less hydrogen gas between each galaxy and galaxies in general in more distinct groups. In essence, this is why we're interested in studying reionization, because we want to get a better idea as to how this happened and why the universe looks the way that it does today. You might be wondering, though, what else does reionization affect? In addition to the transparency of the universe to ionizing light, reionization also affects star formation rates. This is because after it becomes ionized, hydrogen can no longer turn into fuel for stars. This basically means that more ionization means less star formation. The graph on my left from Barkana and Loeb shows this pretty well. These different lines all show essentially how reionization, I should say the star formation would have happened had reionization occurred at different times. On the y-axis, we have our star formation rate, and on the x-axis, we have time in hundreds of millions of years. And essentially, as you can see, sort of depending upon what time reionization starts, we have a pretty drastic difference in how many stars are actually in our universe at the end of things, with no reionization showing a lot more stars than reionization occurring at the start of the universe, which is why we're interested in studying reionization, because it's pretty important for how the universe evolved and how it looks. Okay, so we understand that reionization has a pretty significant impact on how the universe forms, but how can we quantify that? It all starts with parameterizing the evolution of reionization as a function of three variables. Ionizing emissivity describes the amount of ionizing photons entering the intergalactic medium. Its equation is, Its equation is n-ion equals F escape times psi ion times rho SFR. We use this equation to determine how many ionizing photons are being produced and escaped from a given galaxy. For our research, we are specifically focusing on psi ion, or the ionizing production efficiencies. That being said, the fraction of photons escaping a galaxy, which I'll discuss in a bit in the slide after next, and the star formation rate of a given galaxy is also pretty important to the reionization process. Okay, well, it's cool now that we can parameterize this stuff, but why study reionization specifically now? Well, with the launch of JWST, we now have the ability to study the distant universe with new and improved technology. With this technology, we can now study galaxies that were far beyond the reach of Hubble. This is because JWST includes spatial resolution that exceeds that of Hubble. In addition, it also has better near-infrared capabilities, making it more sensitive to redshifted light. This recent advancement is why we're studying reionization now, as opposed to having started earlier. But where do we even get the idea to begin with that ionizing photon production efficiency could somehow be tied to the compactness of these galaxies? Well, what you're looking at now is one of the motivating figures for our research project. It's a graph from Fleury et al., which shows a correlation between two units. The y-axis showing the Lyman continuum escape fraction, or the essentially the production of ionizing photons, and the x-axis showing the galaxy size in kiloparsecs. Different sizes in the data denote data taken at separate observation times, and more filled-in data illustrates galaxies with more significant escape fractions. Anyways, as you'll notice an anti-correlation between the radii of these galaxies and the escape of ionizing light, which is what has motivated us to essentially dive into this project and investigate this phenomenon further. Okay, so we've covered our motivations and a pretty good amount of the background information for this project, but where will we be getting our data? Well, when we're interested in measuring this relationship between size and ionizing photon production efficiency, One of the best places for us to look is places where there's new excellent JWST data. JWST's Advanced Deep Extragalactic Survey, or JADES for short, is an example of a survey in which there were photometric and spectroscopic observations taken. So we have images that I will use to measure galaxy sizes, which come with spectroscopy data relevant to our ionizing photon production efficiencies that we can use in this study. The ionizing photon production efficiencies were measured in Pahl 2024b. The photos were taken specifically in the Goods South field at F115W, meaning in the 1.15 micro, or in a 1.15 micrometer wide filter in the near infrared spectrum. Our filter corresponds to rest ultraviolet imaging for galaxies in the redshift range of 2 to 6. Okay, so now that we have our area to research, we now have to have a tool for actually doing that research, and that is where GalFit comes in. The way that we determine the sizes of galaxies is we fit synthetic 2D light profiles to images, and we do this using a model generation software known as GalFit. It's what we've been spending all of our time essentially collecting the prerequisites for, and it's a tool that actually determines what the sizes of these galaxies are. Basically, what it does is it'll take a science image, a point spread function, a bad pixel map, and parameters, all of which I will explain, and it creates more accurate models of what the shapes of these galaxies really look like so that we can better determine their sizes. When running something like GalFit, it's important to note that the images that we get in our actual telescopes don't necessarily correspond to the true light profiles that come from a galaxy. I don't know how many of you guys know this, but essentially anytime that light enters any sort of optics, it'll be sort of spread out before it becomes an image. And what the point spread function will describe is essentially by how much. The PSF is pretty useful because it helps us to account for that spread inherent to our imaging, so we get a more accurate representation of a galaxy's shape in our model. And for our specific research, we generated a PSF via averaging the light profiles of about 14 stars, and we provided it as an input to GalFit. Nonetheless, not all pictures of galaxies that we want to measure are perfect, and that is where source extractor comes in. Sometimes when attempting to fit a model to a galaxy, we have areas of light that could be interpreted as being a part of the galaxy size, and we need tools that can help us to mask those things out to prevent them from providing misinformation to our modeling software. Source extractor accomplishes this by creating bad pixel maps. Essentially what it does is once we have the cutouts of our galaxy, it'll draw or mask out anything that isn't meant to be the galaxy that we're measuring in these little pixeled out colorful areas. And collectively, these areas make up what we call our bad pixel map. These areas help to ensure that the light we're feeding GalFit is actually from the galaxy in the center of our cutouts instead of some other object near it that could essentially be messing up our model. One of the last things that we worry about with GalFit are its fitting parameters. When fitting galaxies to GalFit, there are many parameters that it'll take an initial input on before it starts its model generation. The two parameters that we care most about are the galaxy's effective radius and the galaxy's axis ratio. The effective radius describes where half of the galaxy's light lies from its center, which we use to determine a galaxy size, and the axis ratio describes the ellipticity of the galaxy, and we will essentially combine those two measurements with math to essentially understand how much physical distance that galaxy in question is occupying. Nevertheless, after we perform a fit, we want to determine whether our Sersic profile or model is accurately describing the light of our galaxy. And for that, we turn to three images. We turn to the science image, the model image, and the residual image. The residual image is one of the more important of the two because it helps us to understand how well our model fits into the original space of our galaxy in the science image. And if these noise levels seem to be about the same or of like a similar composition, we essentially understand that we've done our modeling process correctly, because that means that our model isn't actually adding or subtracting any light from that original space that was occupied by that science image galaxy. So what do we get for some of the results of our galaxy? Well, pictured here are 14 simple morphology galaxies from the early gathering of data about our galaxy sizes. There's a good variation of sizes here, even with this first batch of galaxies, with sizes ranging anywhere from 0.1 kiloparsecs to 2.4 kiloparsecs. While most of these galaxies are simple point galaxies, even in this, it's cool to see that we did have some variations with things like plumes on this third galaxy that would have been caused by things such as like tidal forces. Anyways, after having run these steps on all of our galaxies, we took the size measurements from them and combined them with the appropriate ionizing photon production efficiencies as measured in Pahl 2024b. And to my left is the result of our analysis. While our linear regression fit shows evidence of a negative trend, we performed a Spearman's correlation test on our larger data set of galaxies to yield a p-value of 0.183, indicating a lack of a significant correlation between size and ionizing photon production efficiencies. Should further analysis confirm this lack of a correlation, we could still categorize compact galaxies as being important to reionization, though perhaps maybe not as primary drivers. Moving forward, we plan to include more filters and to potentially extend our sample size by including data from the Sears survey to refine our understanding. Okay, with all that being said, what are the main takeaways for this talk? Firstly, it's that compact galaxies have been demonstrated to have high escape fractions, which was one of the main reasons we chose to research them more in depth, as having higher ionizing photon production efficiencies would have classified them as primary drivers of reionization. Secondly, we use GalFit to measure the size of these galaxies, with most of our work revolving around giving GalFit the right prerequisites for it to function properly. Next, our results from our current research show us that although there seemed to be a relationship between size and ionizing photon production efficiency, we couldn't definitively say, statistically, at least not yet, that there was a correlation. And finally, future work will essentially refine size measurements by including more filters and increasing the sample size via the Sears survey. And yeah, that is my presentation. I will now take any questions.
Hey, thanks, River. Questions for River? Anna?
Back to your results plot. Yes, it looks like there's a number of well-measured ionizing production efficiencies that are low 24.8 and a range of radii. I'm wondering if those galaxies have something else in common in addition to being kind of low in ionizing.
Yeah, so I wouldn't, I'm not entirely sure, but I wouldn't be surprised if there was in fact like something that they did have in common. I know, like, for example, specifically like with galaxies that have higher noise levels, that sometimes will increase like the error bars that we get for those galaxies. But I would probably have to get back to you on that to give you a more like certain answer.
Other questions for River? Mike?
Could you just break down for me how these efficiency numbers are calculated, like what gets fed in, what actually measures?
Yeah, from what I understand, it's essentially we have like H alpha, like I kind of understand, it's like H alpha lines, and we put that over like ultraviolet light, and then we kind of also compare that to the star formation rate of a galaxy. And from that, we essentially get our ionizing photon production efficiency. I don't understand the entire process, but it is kind of something along those lines. And then we essentially go in and we compare that to our sizes. So.
All right, let's thank River again.